Hi and welcome to Unit 1, Topic 3, Video 21. We're going to look at chord theorems. This, of course, is a continuation on our work in circle theorems. You've learnt 4 circle theorems in an arbitrary order, 3 tangent theorems, and now we're going to look at 2 chord theorems. So there are 9 theorems in total. Now, again, you won't have this information. It is Unit 1, so it may come up in Unit 3-4 external exam, but it's a little bit trickier to get into that external exam, so it's less likely, but still possible. But you won't have the chord theorems on your formula sheet, so you kind of need to know these theorems just like the other circle theorems. So starting with Theorem 8. Theorem 8 states, if A, B and C, D are 2 chords of a circle that cut at point P, which may be inside or outside the circle, then PA times PB equals PC times PD. So we have our theorem that relates multiplying this chord and this chord to get the same value as multiplying this chord and this chord. So the chord pairs on the same line, but they're split where P is. And we get the same result with our P on the outside, except this time we're multiplying PA, which is that long one, by PB, which is that short one, and then the same on the other side, so PD and PC. And we should get the same result. So this is a rate ratio-based relationship, which you can rearrange to get a really nice ratio. But it's nice having it this way as well, because then we've got PA times PB and they're on the same line. Okay, so let's have a look at a proof. And for this one, I'm going to use diagram 1, but we could use diagram 2 as well. And just a heads up, if we use diagram 2, we're going to prove that APD is similar to CPB, and it's going to look pretty much exactly the same. So what I'm going to do is I'm going to add some dotted lines here. I cannot make any assumption about parallel lines as much as I want to, but what I do have is I have some angles, such as these two, that are equal because they're off the same arc, and these two that are equal because they're off the same arc. So the red ones are off arc AD, and the green ones are off arc CB. So I can make these statements. Angle ACD equals angle ABD. This is angles off has 2 F's, same arc. And angle CAB equals angle CDB, also angles of the same arc. It's a little bit lazy of me, but there it is. And also angle APC is equal to angle DPB, which is pretty much given anyway, but they're vertically opposite, so I can use that. And therefore, triangle APC is similar to triangle DPB. And the reason is angle, angle, angle. So we've established similarity, which means we can also establish ratio pairs. So that means that the ratio between equivalent sides in the same triangle is equal. So there's a few ways I can do the ratio. But what I'm going to do is I'm going to say that AP over CP is equal to DP over BP. So this side here and this side here match because they're adjacent to the green angle and the central angle. And these sides match, so they become my denominators, they become my numerators. Doesn't matter which way around I do it, because this ultimately leads to AP times BP is equal to CP times DP, and that's what we're trying to show. So we have proven that Theorem 8 is true, as you can see from the original proof. Now you probably won't have to show the proof, but you just have to understand those ratios exist. We'll get the same result with the second diagram if you want to have a look at that. Theorem 9, on the other hand, is if point P is a point outside a circle and T, A and B are points on the circle such that PT is a tangent and PAB is a secant, then PT squared equals PA dot PB. So this comes in a very similar fashion with similarity, and it's really a likely extension given that PA times PB is a full part of our last question. So another way we could do this is we could say, we could draw another line here and have this and this. We've got 2 chords, PA, PB, PC, PD, and we could link up that way. It's a little bit trickier though because PT is still standalone. So let's do some work with our similarity then. Okay, so firstly we have, and I'll just create a little bit of space. First we have this, angle PTA is equal to angle TBP. So in pink, that's this angle and this angle, and they're equivalent, and that is from the alternate segment theorem, which is one of our tangent rules. That's a T, so alternate segment theorem. So go back and have a look at that if you need to. We also have that angle TPA is common, and I'll show you the triangles in a second. And so therefore I can say that this triangle here, which has the pink one and the common angle here, is congruent to this triangle here, which has that pink one and the common angle as well. And we can make the statement, just through simple subtraction, that this angle here, I might just rub out some of this blue stuff, this angle must be equal to this angle. Sorry, that's not right. This angle here, my apologies, must be equal to that PTB angle, just from similarity or from subtraction of the angle sum of a triangle. So we've got those two angles that are equivalent, which means three angles must be equivalent, and therefore triangle PTA is similar to triangle PBT. And from that, we can make the statement, keep in mind our similar sides, that PT is here, PT over, so that's the one adjacent to the pink and the red, over PB is equal to, what's equivalent to PB? PB is between the red and the pink, oh, so no, and then is equal to, let me write that down, PT over PB is equal to PA, so that is now this side in our smaller triangle, over PT, which is the long side in our smaller triangle, so PA over PT, and when we rearrange that, I get PT squared is equal to PA times PB, as required. So there's our two proofs of theorem 9 and theorem 8. Let's look at a couple of examples, and then we're done for circle theorems. So, example 9, calculate the value of y. So we recall that we have a relationship between, and remember because there's a point on the outside, it's the short length and the long length. X is the important connector, short length, long length. So that means that in algebra, xd times xc is equal to xb times xa. X is our p in this case. So xd is 6 times 6 plus y, that's xc, is equal to 7 times 7 plus 5. Easy question to mark up here because we've got a point on the outside, we have to do some addition to get our xc. So y and 5 are none of our side lengths that we're talking about here. This gives me 36 plus 6y is equal to 7 times 12, which is 84, which means 6y is equal to 48, and that means that y is equal to 8, which is a perfectly reasonable solution. So there's our first example, and here's our last example. And it reads, prove that if the radius bisects a chord, then a radius meets the chord at right angles. So let's have a look. We'll start with a circle, and we'll set up a diagram. So I'm going to put my chord here, and we'll call the chord AB, and I've got my centre here, which I'll call O. Now, to form part of this proof, and I think there are multiple ways we can do this proof, but we're going to use chord theorems. So I'm going to start by marking this point here, which is the point that bisects AB. And then I'm going to draw a line that goes directly through that point and through the centre and all the way to the other side, because that produces for me two chords. Now, what I'm trying to prove is that this is a right angle. That's the ultimate goal here. And to do that, I'm going to set up one other little line here. And this will help me a little bit later on. And I might need AO as well. Let's just see where we go. Okay, so I've got a few things I know first of all. I've got AO, and I should do some more labelling. Let's call this C, and this D, and we'll call this central point here E. AO is equal to CO is equal to BO is equal to DO is equal to R, the radius. So I'll mark it on here. That's my length R, whatever that is. I know they're all equal. I also know that AE is equal to BE. That's the fact that my chord is bisected. And I'm going to say, just to help me out, OE equal X. So we'll call this bit here X. So what I have is X, and this length is R, and this length is R minus X because CO is a radius. And then I've got R, and I've got BE and AE. So from my two chords, CD and AB, and chord theorem 1, I've got that AE times BE is equal to CE times DE. Now I know that AE is equal to BE, so let's call this BE squared. And that's equal to CE, which is R minus X, times by DE, which is R plus X. Now, I've got R minus X and R plus X, so that is R squared minus X squared on the expansion. It's equal to BE squared. I could give BE a name here, but we're almost done, so I don't really need to. And so therefore, if I add the X squared to both sides, I get BE squared plus X squared is equal to R squared. That is, BE squared plus X squared is equal to R squared. That's the Pythagorean relationship, and that relationship only holds in right angled triangles. And therefore, the angle between the two shorter sides, BE and EO, or BE and X, must be a right angle. So we can say, therefore, due to Pythag, and if this was an exam, I'll probably take this a little bit longer, but due to Pythag, angle BEO equals 90 degrees. Now we know that AB is a straight line, so that means that AEO is also 90 degrees, and the radius meets the chord at right angles, if and in any case where the radius bisects the chord. So there's our two chord theorems and a couple of examples of how to apply them. All the best.